First of all, I warmly welcome you all to the fourth session of online webinar series 2021 powered by SET Sabra, collaborated with SET Sri Lanka. So as you already know, this annual webinar series basically focuses on dynamic individuals like you who are planning to represent Sri Lanka on international platforms. So if you are such a devotee, just stay connected with us because today's session on airborne laser scanning and reconstruction of 3D topography surely will be a productive, beneficial and beyond price. So today we have a genius personality in this field who is going to share his precious knowledge with you. But before starting the session, I would like to let you know that there will be a Q&A session after this, and there you can clarify all your issues regarding this session. So, without wasting much time, I would like to hand over the session to today's guest speaker, Dr. Sanka N. Perera, a senior lecturer of Department of Remote Sensing and GIS of Faculty of Geomatics of Sabaragamu University of Sri Lanka. So, it's over to you, sir.
Okay. Okay, many thanks, Chamini. I think everybody can hear me. Okay, so and also many thanks for inviting me, SET Sabra, for taking a let's talk about the laser scan and our specialty about laser scanning. And I've chosen laser scanning and reconstruction 3D topography. Probably that could be a very hot area, and because the comparing to the current world, the laser scanning become the most promising data acquisition technology, geospatial data acquisition technology in the world today, because when compared to other data such as the image data, for data captured by the laser scanners have high automation power than the all other types, and also high accuracy, which leads to be more popular among the community, user community of the data acquisition methods. Okay, and actually, primarily the laser scanners can be mounted in either airborne or the ground-based platforms. In the case of ground-based, that could be a tripod-mounted terrestrial laser scanners or the mobile moving platform, the mobile laser scanners. And actually, the space-borne platforms are not much popular because things are still under development, and so we'll move further. Okay, and actually you can see in my first slides, the cover slides, and you can see some nice colorized trees. Actually, these trees, each color represent different each individual trees actually. And these are nicely captured by the moving laser scanner, mobile laser scanners, and these facades also captured by the mobile laser scanners. And the bottom figure says the nice example of the data captured by the airborne laser scanners. And since these are having certain colors, which means and which we have added additional attributes, actually we classified these things, and we'll talk about these things a little later. Okay. So I would choose these contents, and first I would talk about a little bit about the basic measuring concepts and the propagation characteristic of the laser, also the essential system components of the laser scanners and the flowing clouds and the errors, and how we can reconstruct the 3D topography and so on. Okay, so actually you guys have heard about the rather than the laser scanning, you guys have heard about the LiDAR or the LiDAR, also the laser scanners activities. And question would be is it a matter? Actually, it's not a matter. The different though these different, actually the different communities basically use different terminologies. And the LiDAR, it's an acronym, stand for light detection and ranging, basically used by the atmospheric research groups. And the LiDAR, it's basically used by the military people. The laser scanning is basically used by the photogrammetrists or the geometricians as the majority of the geometric people. And since the scanner measures the altitude, so the altimetry instead of the scanners, the altimetry, the term also used. Okay, so then the next question would be the what is LiDAR or the laser scanning? Actually, it's a active remote sensing technology which measures very dense, great position and information, including the Z across the landscape, whatever the shallow water or even industrial sites. It doesn't matter whether it is outdoor or indoor, which measures very accurate dense point clouds with data sets. So that the day and night observation is possible, but keep in mind that the point clouds, also the laser scanners is weather dependent. It's not like the micro remote sensing is weather dependent, and we may not be able to capture the data by the level laser scanners or whatever the terrain scanning the ground-based systems. In the case of the rainy days or in the cloudy, not in the cloudy days, in the airborne laser scanner, but the ground-based is okay. And the foggy days, because these influence of these factors make more influence rather than the clear days. Okay, so before moving further, I would a little bit talk about the electromagnetic radiation that is being used in the system, the laser scanning system. Actually, it's laser is also it stands for light amplification by stimulated emission of radiation. Actually, from the industry, we can recognize different types of laser systems. These are classified based on the material which are being used to emit the lasers. Basically, the gas laser, solid state, the semiconductor lasers are the commonly find the methods or the techniques or the scan types. But the last two, the solid state and the semiconductor, these two laser types are more widely being used in the laser scanners. Actually, the neodymium doped crystallite yttrium aluminum garnet basically used to generate the exactly 1064 nanometer wavelength pulse, which falls within the electromagnetic spectrum in the infrared region. And by frequency doubling with the same material, that is 532 wavelengths, the green lasers can be generated, which falls within the visible range in the hexagon on the green. The green laser is basically used in the bathymetric LiDAR scanners. The semiconductor systems use the gallium arsenides basically. So the question would be why the laser? Why not the infrared or whatever the others? The specialty of the laser is it emits monochromatic directional and the coherent pulse or beam or the continuous waves. Monochromatic is the wavelengths are whatever all the pulses, the wavelengths are almost same. The directional is having the propagate with a very little divergence, and the coherents are the pulses are propagate in phase. So this figure says the onboard the helicopter mounted the scanner systems, which repetitively generates the pulses, which enables to measure the information on top of the terrain, and the system which is inside able to measure the range between the target and the platform with the help of you can see then there's a ground-based station, ground-based GNS the receiver, and on board receivers, and also on board UMU and things there. We'll talk about what is the role of each and every component. Okay. Actually, in laser scanners, it doesn't matter whether it is the ground-based or the airborne. In laser scanners, they're basically two different types of waves. That is the discrete pulse or the continuous waves are used for the measuring purposes, to measure the distance between, or the range between the platform and the target where the returns come from. In the case of discrete pulse systems, the range is measured by measuring the travel time, or you can also say that time of flight. Because of that, then you can also say that the time of flight measuring concept. Okay, as you can see, the pulse has a certain pulse width. Say the pulse width, the time for the pulse width is, say, TP, and also it has a very short, very narrow rise time, pulse rise time, say the T rise. For example, if I say the pulse width is equal to, time is equal to 10 nanoseconds, in the range wise, it is nearly 3 meters, and the pulse rise time is something like nanoseconds, so it's something 30 centimeters. Okay, then since it measures it's a two-way, it's transmit from the transmitter to the target, and from the reflected return signal is also received from the receiver. There is a two-way transmission, and there is the range is twice. Range is measured by the travel time. So then the travel time would be is the ratio between 2r by c and the c, if this is the velocity of the wave pulse. Now, for example, when the range is 1,000 meter and the travel time is nearly 7 microseconds, so then we can also neglect the whatever the pulse width. And actually, the range resolution, that is accuracy of the range measurement, basically rely on the accuracy of the time measurements. So that even the laser scanners, in the discrete pulse laser scanners, the accurate time intermeters are on board. Okay. Though the laser pulses are very narrow and very highly coherent, as soon as it emits from the aperture, it's diffracted, that means it's having a little divergence. It's the pulses propagate. Because of that, the considerable of wave front is propagate a considerable area, and which enables to provides more returns from the targets which locates within the line of sight to discriminate to consecutive returns. And the return wave pulse, return envelopes, there should not be any overlap between the return envelopes, which means, say the first return comes from up to the T1, the second return T2, the time difference T2 minus T1 should be less than to the pulse time, pulse width. So then by substituting the ranges, to discriminate these two coming from two different returns, coming from two different targets, there should be the vertical separation should be greater than the half of the pulse width. If the pulse width, which is equal to 10 nanoseconds, that is 3 meters, which means nearly the 1.5 meter is the vertical separation that can be separated in a single pulse. And it doesn't say that the features which are lie within the 1.5 meter cannot be measured by the Airborne scanners. Actually, that can the measurements are done with the other pulses, not by the this is the what I said is the one single pulse. Actually, the laser scanner generates the pulses repetitive at a very high frequency. Okay. So in the case of continuous waves, the modulation techniques are being used to measure the range. Actually, the measuring wave is superimposed with the carrier wave, and which is then modulated, and this modulated the wave is transmitted, and then once it reflects and back to the receiver. Once it received, the received signal is demodulated and compared with the original transmitted signals, and in order to get the pace comparison, the pace shift between transmission and the reception. Okay. Actually, the onboard in the continuous wave case, the pace meter is what, and which measures the fraction of the paces, the entire one cycle, one complete wave, one cycle. The pace difference is 2.5 or the 360 degrees, and the portion of the path, say the delta phi, is the pace difference, pace shift, or in the entire the journey, the total pace shift would be the m number of cycles plus the portion of cycle, that is equal to the m times 2.5 plus the delta phi, and that can be also be converted, or we can also derive the range equation in the form of R is equal to m half lambda plus this delta phi half lambda is that one. Okay. The pace meter measures only the fraction parts. The issue is to solve the ambiguity of the or the complete cycles, the number of cycles. The determination of the M is the issue now. Actually, the M is solved by transmitting multi-frequency waves, and starting from the short wave, the high frequency to the low frequency, that is the long lambda. And the one time the range is fully covered by one cycle, or the entire range can be brought inside the entire cycle envelope. That is which is measured by the pace meter. That is the coarse, but which is the value is very coarse result, coarse range, which can be rectified or corrected by transmitting the little less, the wavelength having little less, the wave having less wavelength, another wavelength likewise, and after just by shifting this little computation, these can be solved. I think those who know the measuring techniques of the total station or the EDMs, the same concept is used in the continuous wave cases. I would not discuss this much, and because that would be very new to the other people, unlike the geomatics. Okay, so I would let's talk a little bit about the propagation characteristics of the laser. So now it's clear that as soon as it emits from the aperture, the laser pulse, which is diffracted, which means which propagate with a little divergence. If the divergence angle is gamma, and theoretically the refraction is given in the ratio between the constant, the lambda, with t, and generally for the wave having pulses having the wavelength 1064 nanometers, the aperture diameter is 10 centimeters. The divergence angle is nearly within milliradians, nearly 0.3. Compared to the entire laser scanners which exist in the industry, the divergence angle is less than milliradians, 2 milliradians, say. So then the ground diameter of the beam footprint is nearly fall into the h into gamma. So then in the case of flying height is 1 kilometer, then the beam footprint, the diameter of the beam footprint is nearly 30 centimeters. Okay, that is also nice to need to know, and also think how the power is propagated. Okay. Actually, at the time of transmission, the pulse is transmitted with the power, say P transmitted. The transmitted wave is interact with the the particles in the atmosphere, and also at the target surface also interaction happens and absorption happens. Also in the return journey, certain the same again interaction happen with the atmosphere, and these interactions actually lose the lots of energy. What is received is very less, and I would put some values, and I would for you to understand this. And if the transmitted power is PT, and what is received is which is rely on the transmission factor, say m into PT, and what is received, and what is, say, that is the if the diffuse reflection is taken place at the target, so then the what is reflected is given with its little values, and what is received is given here. For example, if the transmitted power is 2000 watt, and what is received is at the end is 800 nanowatts, that is very less, which means the laser rangefinders or the laser diode should transmit the laser pulses with very high power. Otherwise, it will not receive to the receiver, or maybe the receiver may not be able to recognize this as a strong or the return because it is very weak. Okay. Okay. Since we talk about the power losing, and the reflectivity is another important factor. Okay. Actually, what is reflectivity? So reflectivity is the percentage of energy reflected by the target with respect to the received energy, what is received. As you can see in the previous case, and the reflectivity is always proportional to the range, which is also shown in this graph. The highest reflectivity is given by the dimensional lumber. Lumber is the pine tree, which is when one cut with the saw, and when it's dry, is the highest reflectivity is given, and the least reflectivity is given by the rubber. That is always almost absorbed. And the reflectivity is the strength of the return, which is also commonly known as the intensity. And some laser scanners, not all the scanners, and actually the modern scanners are able to measure the strength of the return, that is intensity, which is also recorded and stored as an additional attribute, and it is displayed so in the form of points. Can also be in the form of raster, can also converted as in the form of rasters, and the place where the dark location shows where the less reflectivity targets are. Okay, if I talk about a little bit about the interaction with the target, if the incident wave is illuminated by a certain flat surface, and within the footprint, since now you know that it's a divergence, the beam is having the little divergence, and footprint is nearly, say, the 1 feet diameter. Within the diameter, the entire target area is homogeneously reflective target. Say the return is almost same. There's no strong return at one location. Since it is almost flat, the returns goes back at the same time, which means which tend to get a very strong return with a very short, very narrow rise time. So then, which means the flat surfaces are measured at very high accuracy. Say what happened to the irregular surfaces. Okay, in the case of irregular surfaces, for example, the vegetation canopy, not much high vegetation, very low vegetation, say, for example, what happened is and because of the beam divergence, and the wavefront is sufficient enough to get several returns from the several returns where several obstacles would lie within the line of sight. So several returns will be taken place. If all these targets lie within a half lambda, that is half of the pulse width, which means the return pulses are always having the same within all these envelopes are short with having sort of an envelope. I mean the overlap. Because of this overlap, what is finally the resultant the envelope V1, which have a very long pass rise time, very long rise time, is the just nearly equal to 7 nanoseconds. 7 nanoseconds is nearly more than 2 meters. So then the positional accuracy, actually the elevation accuracy, range accuracy of that particular area, the measurement is very less. That is less than 2 meters accuracy, which means okay. So now you know then in the case of flat surface, the almost same accuracy is given. In the case of slope terrain, if the closest and the farmost edges, the locations, exceed, goes beyond the elevation, the minimum, the separable distance, that is half of the pass width, then this definitely, even though this this is a one single target, the single objects, these two are recorded as two coming from signals returns coming from the two different targets. What happens if the high reflectivity target is exists next to low reflectivity target? So then, even though the high reflectivity target is exists locate little less or is lower than the other target, these returns more strong enough than what is received, what is reflected by the less reflective one. The same for the slope terrain as well. No? Okay. So also, there's one thing that we should also talk about. That is the effect of scan angle. That is the scan angle. The increasing of the scan angle worsen the canopy transmission. The laser doesn't penetrate through the canopies; it's passed through the walls of the canopies, because several obstacles would arise. Then that is transmit in the nicely beneath or the nadir view, the nadir direction. Several obstacles happens, and there's less opportunity to reach to the ground. Okay. Similarly, when increasing the scan angle, the occlusion effect is also increased. Also, with the same reason, increasing the scan angle also escape the returns, the reflections from the receiver in the case of the target, if the target is covered by the specular reflected objects, for example, the water feature, which means the water feature is no returns, there's a gap exist. Okay, now I would like to talk about the essential components of the analysis scanners. Definitely, there should be a device to transmit the laser pulses. That is the laser head. Also, to measure the travel time, should be a precise timer or the pace meter, and also to measure the attitude changes of the platform changes. The initial measurement unit should be there. We'll also talk about what these are and what the role. And there should be onboard DNS to measure the onboard positions and the real-time positions while it's transmitting, while it's flying with the trajectory. And also there should be a scanning mechanism that is to widen the viewing area. Also, generally we process the DNS data and the differential DGPS techniques, so that this would be a ground-based station. These onboard devices are linked to one system called the control system. It's called control rack through the cables, and there are two. When I talk of the crew, and the minimum crew is the two, and the pilot and the navigator, and they are guided with the help of the interfaces. These are the essential components. So we'll talk about a little bit and each. And actually, in the airborne laser scanners mainly use the diode pump solid state. That is the neodymium of the crystalline yttrium garnet solid state materials to generate the lasers. And the modern systems and the pulse repetitive frequency, that is, the lasers are repetitively transmitting one after the other at a very high rate, that is which is known as pulse repetitive frequency. The modern systems, the repetitive frequency is very high, is close to the 2000 kilohertz. In the earlier systems, it's very low, it's 50 kilohertz something. Okay. Generally, it generates the low, very narrow beams. That's okay, obvious. Okay, and also the initial measurement unit is also an essential components which basically contains the accelerometers and the gyros, and these are the two integrated devices. Accelerometer used to measure the relative translation, that is the displacement along XY Z directions, the relative motions in all those directions, and the gyros used to measure the rotational changes along XYZ axis, that is the roll piece cut by you. Actually, these observations, the accelerometer and gyros measures the attitude at a certain intervals, at a certain sampling rate, and for example 200 hertz, which means within 1 second 200 times is measured at a certain interval. It's depend on the range. The length interval is depend on the speed of the aircraft. Okay. It's onboard DNS, and which used to measure the onboard location and position, and also used to do the post processing as a DGPF, and also have sampling rates. Generally, I remember that actually the recently, a couple of years back, the Fugro is a very famous company, came here to do the LiDAR survey, and they configured the DNS the 1/10 epoch. The epoch time is the sampling rate. Okay. The scanning mechanism is another essential component, which is basically used to widen the viewing area. Otherwise, without scanner, what happens is the rangefinder repetitively generate the pulses, and the aircraft move along one direction along the flight line. What happens is it only scans along one line. That is, the profile scanning happens. It's not worth, and it's always worth is to scan the very wide areas, and that's why I use this scanning mechanism, similar to spaceborne platforms. That is the along track or the cross track, or actually the whisk broom or the push broom mechanisms are being used even in the airborne laser scans as well. The oldest scanning mechanism is the oscillating mirrors, which oscillate across to the flight direction. Actually, they're orthogonal to the flight direction because of the oscillatory motion, which end up with the sawtooth scan lines on the ground. Okay. And the sawtooth scan lines, which means these are the place where the scanning happens, and there are several gaps exist. And then now you know that the scan at a certain locations, not everywhere, which means finally we end up with the measurements of kind of spot locations, that is the point, so known as the point cloud. And the density of the point cloud is not uniform, and because of that, people wanted to get the kind of a uniform point densities, something similar to the raster data. To get the uniform point density, what we should do is to stop the opposite rotation. So what we should do is to let the mirror to rotate in the same direction. And then the people use the rotating mirrors, sorry, the polygonal mirrors. Instead of the oscillating mirrors, use the polygonal mirrors, and several mirrors are stick to the polygon, and the polygon rotate in the only one direction. Okay, which leads to the parallel scan lines. And these are across to the flight direction, and also there's a kind of a fixed array of fibers. Fiber switch is another one, and a fixed array of glass fibers are used to transmit or to emit the laser pulses simultaneously at once. And with advanced motion, the next area likewise the area by area is scanned, line by line is scanned, which is almost same to the push broom method. And since the fixed array is very less number of array, the 128 is mainly, this method is mainly used by toposes. These are only people who use the fiber switches, and the narrow scan area is. And the other one is the notated mirror of the Palmer scanners, and this is a little modification to the oscillating mirrors. Okay. And these are the scanner types, and the sawtooth pattern is given by the oscillating mirrors, and the parallel scan lines is given by the rotating polygon mirrors, and the also the push broom types, the fiber switches is all given the scan lines, which are exactly orthogonal to the flight direction. These are having little inclination because of the speed of craft. And the rotating mirror is the specialties in addition to the usual what you call the oscillatory motion. The mirror is simultaneously rotate along its own axis, which leads to generate the circular scan lines. But with due to the advanced motion, the circles become the elongated ellipse. So then the elliptical scan lines we end up with the elliptical scan lines. Okay. This is kind of a control rack, and with the power cables, the cables and everything, all these devices are linked to this control rack, and also the external devices and the data storage medium and everything is installed inside within this unit. Power on off, shutdown, and the booting, and also everything is controlled by the switch patterns, and everything is here. And this is an onboard hard disk. Okay, and these are the two interfaces. This smaller one is the pilot interface. The pilot sees only the heading direction, and the navigator is able to control everything. Navigator is controlled with the help of softwares, navigation softwares. And for example, this is what is inside the onboard platform. Here you see, as you can see, the progress of the scan and what is the next scan line, everything, and the scanning parameters. And this is place where you can change the scanning parameter, and everything can be controlled by the navigator. Okay. If I talk about the platforms, both the fixed wing and the rotary wing, that's the helicopter type, the platforms are being used, and they are more or less scanning. The fixed wings are basically used. Actually, these the aeroplanes can fly at high altitude and also at a high speed. Because of that, very large, in the case of large areas, I scan to scan the very large areas, basically use the aircrafts, aeroplanes. And while if a client needs high density point clouds, that is the platform should fly slowly. And also, if in the case of urban, something like high-rise buildings, and then the safety, and also the narrow corridors or the narrow valleys, and these things, these are the place where the careful the flying should be taken place. In these situations, and the helicopter type platforms are basically used. Okay, so suppose now the flight mission is completed, and then is captured the data. Then the processing unit would receive the onboard data set as well as the ground-based data. So the onboard data, say we can say that contains everything together, say the range files, or what is containing inside the onboard data. It contains the data measured by the range finder, that is range data, also the time tags, and also the scanner mechanism, what is scan angles relevant to each and every transmitted lines, scan lines, other paths, and also IMU, which measures the attitude at certain location, and the GNS also measures the position, platform position at certain locations. Actually, these are the basically contains in the onboard data. First, the first intention is to find the trajectory. Therefore, we should extract the GNS data, actually the position data. Position data means the post data, say, okay, the IMU and the GNS data. So first we should decode the range file into the range data, that is the data relevant to the range, that is the range measurements, time tags, and the scan angles, and the position data, that is post data, that is IMU plus DNS. Thus we decode. Actually, the point cloud generation is taken place with the help of series of software modules. Then the extraction, for the extraction, sorry, for the decoding, the kind of module is used, and once the post data is taken, the IMU and the ARDNs. ARDNs data should be extracted from the post data. Then the idea is to do the GPS together with the ground-based data. So once we extract the onboard data, GNS data, we can do the GPS differential post-processing together with the base data, and then we'll get the flight trajectory, but which is very cracked because of the turbulence and the errors and the rotation and torsion and things, and that should be corrected by the IMU attitude corrections and the rotation angle or the translation shifts, and all the attitude changes are measured. Since we should apply the correction to this trajectory. Once we apply the corrections, then we will get the smooth base estimated trajectory, that is called the short for SBET. We'll get the SBET. Having the smooth base trajectory, then what we need is to then get the point cloud. Then we have the range data and also the scan angle data, the scan data. Knowing the SBET, which means we know whatever the location, trajectory means we know any position along the trajectory. Though the GNS measured the position at certain intervals, and the IMU measures the attitude at a shorter intervals, sort of interpolation is taken even in the SBET generation. Within the process of point cloud generation, again the interpolation is taken place, and the knowing the range and the scan angles, and finally we end up with the point clouds, the position of the location or where the return came from. Okay, so we have the point cloud. This is basically in the with respect to WGS 84. So the next step is to coordinate transformation to our own datums. Okay, this is look like the raw point clouds. So this is the perspective view, and the bottom one is the aerial view. From the aerial view, we can't see anything, and we can't recognize anything. Basically, from the perspective, we can see some power lines and the towers, and also some buildings, several things. And this is not like the image satellite data or the image data. Image data shows the spectral characteristics of the targets, but in here only additional information is the reflectivity, which is not much useful than like the spectral signatures. Okay, due to the little divergence, now you know that the several returns would arise when then the canopy is irradiated by the resistance pulses. Basically, the first return always coming from the top of the canopy, and the several intermediate returns come from the once it hit the branches, leaves, or whatever the intermediate things, and the last return would definitely come from the terrain. Actually, the scanner systems are able to record the tags the number of return, the return number. This is return number, which means first return is the return number. Return number 1, return number 2, 3, 4, likewise, tags. By calling the return tags, the software is able to visualize only the first return, second return, or altogether, likewise. Okay. This is an example of the entire point clouds, all returns together with the entire point returns. And actually, in addition to this is not the raw, actually this is classified data set. That's why you see the points, vegetation point in green, and the whatever the last bottom line, actually, which is the terrain. This is only a profile. Actually, this is somewhere in the within Mahaveli Basin, somewhere in Sri Lanka. Okay, and as you can see, beneath the vegetation, the terrain is given, which means the laser pulses pass through the holes within the canopies. This is the specialty of the laser, and in the photogrammetry drone, whatever the other methods are not able to generate or to provide the information beneath the canopies. Only the laser can do this. Okay, here you see some gaps. Why the gaps happens? Gaps happens when the returns reflect from some kind of a hard surface. Hard surface are the stems. So the place where the stems are, there are gaps. Okay, these are two examples that we can see the return, all returns with the last return, and this is the nice one. And once we visualize the all returns, these look blanks, and once we visualize only the last returns, we can nicely see the vehicles parked beneath the vegetation. And also now you don't see the kind of fence or something. Actually, this could be a flower bed or whatever, the live fence or whatever, or vegetation at some point, kind of a vegetation fence, and which is, since the last return, which is disappeared, which there's no return from the vegetation in the last return. Okay, this because of that we can recognize the place where the vegetation and where not the vegetation from the by analyzing the first and the last and things. Okay, this is an additional thing. Okay, actually the modern laser scanner, actually in the modern laser scanners are able to record the entire full waveform, not like in the discrete process and in the discrete systems. And nowadays the discrete systems are able to record up to 8 returns, 4 to 8 returns, say. In the previously, in the initial time, on the first return, then the first and the last return, and then in the discrete case also, in the first, last, and the several few, and up to 8 is able to measure. But there are another group of laser scanners which is able to measure, which is able to record the entire waveform. And then how do you get the data of the point cloud from the entire waveform? Then we should sample this into an equal something like the 10 centimeter intervals, and you should do the equidization, and then by fitting the Gaussian models and things, and we can get the point cloud. And what is additional that we received from the full waveform like is we'll get some additional information or the hint about the shape of the targets. For example, in the flat group and the flat surface, there are strong returns, which means the peak is very strong peak, and there very high peak with the less width or the narrow Gaussian. And in the case of the slope terrain, and which is a bit elongated one, by analyzing the shape of the Gaussian models, and we see that okay, this is flat surface and this come from the slope terrain. These are something additional. Okay. Okay, and then you know that the neodymium dope, the lithium crystalline lithium aluminum garnet, the solid state diode pumps materials are being used to generate the laser pulses. In the case of topographic measurements, is used in the 1064 nanometer waves, And by frequency doubling this with the same material, the same cavity and the same the diodes and everything, by frequency doubling, the green laser is generated. The frequency doubling, which contains high power with high frequencies, which because of the less attenuation, the green laser is able to penetrate through the water column. The refraction, everything is happened. That is okay. Then refraction correction and several corrections should be applied in order to get the accurate depth information. That is something else. And the normal the 10,064 nanometer laser say actually switch force the infrared region, say which look the green, the reddish, and the gray laser reflects from the water surface. And this is an example of the themes, the mathematic information, or the mathematic of depth information of the themes really. Okay, so how do you visualize the point clouds? Actually, we can visualize the point clouds in the form of points and as well as in the form of rasters. To visualize the point cloud in the form of rasters, first we should convert the point cloud into the raster. How do you do it? Actually, we can do the conversion. We can do several ways, and the beginning and several, but I would say the most accurate one. And first, we can make the twin mesh from point cloud. Then the grid template can be superimposed on top of twin mesh. And what we need is to fill the elevation values to each and every cells. Having the twin mesh, we're able to interpolate and able to determine or to compute the elevation of the center of the cell or the elevation of the corner of a cell. Which means, and we can fill once we fill up all things, and we'll get the raster elevated image, which looks like that. Then by assign the kind of a color circle, RGB or grayscale, whatever the color circle, we can visualize the elevation raster. That could be kind of a elevation model. Digital elevation model is also known as the elevation model. Okay, so or can also use the additional attributes. These are the intensities, and intensities can be colorized. Intensity values colorized with respect to the point cloud, or also can also be can get the raster intensity data sets by the conversion as previously. Otherwise, we can straight away use the point clouds and generate the twin mesh, and these twin mesh can be filled with the faces and can be get the solid surface. And so this is kind of another point rendering techniques. And this is also the twin mesh of this perspective view of the point cloud. This is of course the surface, digital surface model. Okay. And these are the superimpose of the point cloud on top of the twin mesh relevant to the digital trend model. So then you can find the elevation changes of the canopies and the terrain, and nice you can recognize these. And one of the most popular visualizing technique that people are now being used is colorizing the point cloud. To colorize the point clouds, we have to rely on kind of color images, and the most famous and the most accurate one is to use the orthophotographs, orthophotos, so that we should overlay the orthophoto top of the point cloud and over the other way. And if we take one single point and the pixel which is closest to that particular point, and you can get the RGB values of that particular pixel and then assign that RGB values to what we have selected point. This is how we can colorize the it is just kind of a nearest neighbor assignment, and could be same pixel same value would assign to several point as said. So overlaying over or the repetition and things happens. These are approximations, so there's no way other way. Okay, so let me talk a little bit about the errors. I think everybody is with me. So I will go further. Okay. Actually, now everybody know that the onboard platform, what is on board is the IMU scanner mechanism, GNS, and also the rangefinder. And these are the essential components that are mounted on board. Actually, these are independent devices, operate independently, and also mounted in different locations. For example, IMU has its own axis, and also the scanner mechanism also has its own axis. Okay, but one thing that you should know is as soon as the one mission is completed, and then you should dispatch, and you should remove all these devices and should send to the stores. Once you need to do another new LiDAR survey, then you should install all the devices. Okay, this installation and reinstallation and dispatching and removing, and these things also tend to have kind of a misalignment, misinstallation, installation with little misalignment, and also there is kind of sometimes could be manufacturers would happen. It's from the beginning, and also the wear and tear, and because of several issues, all these devices would contribute kind of errors. These could be the systematic errors or random modems, whatever the things. Anyhow, at the end, what happened is all these errors are contributed and accumulated, and at the end, that will be influenced to the XYZ portions of the point cloud. Okay. The most critical errors, two errors, are the misalignment between the IMU axis and the scanner mechanism axis. Actually, the when it's reached the ideal situation, there's no misalignments. All these axes are properly aligned, properly almost parallel. There's no alignment, no, I mean, the synchronicity happens. Same thing, but losing of the screws or whatever, the misalignments or tightening of one screw or something would tend to kind of a relative change, relative misalignment with respect to one to other. In the case of misalignment along the XYZ rotation angles, or it's with respect to the angular misalignment, is known as the Bose-side angle error. And also also possible to happen even though we firmly fix the things, there is a fixed offset between the IMU and the scanner mechanism, but due to the misalignment, these fixed offsets will be deviated along the XYZ directions, and these led to changes, misalignment in translation along all three axes. Would also make some errors, which call as the leave-arm distance error. And these are the more critical alignment errors. So then we'll see what are the other error sources. Okay, actually, what is on board is the, for example, is a scanner, the rangefinder. Rangefinder transmit the pulses, and who knows that the range measurements are more free from the errors. Probably the measuring errors, ranging errors would be there. Actually, the range errors influence to the range errors influence to the planimetric position as well as the elevation. And also the scanning errors, that is kind of an angular error. Scan errors highly influenced to planimetrically rather than the elevation. And the misalignment between which is already talked about, the IMU and the scanner, these two errors are Bose-side and the leave-arm errors are also there. And also the misalignment between the GPS and IMU should also be there. The relative changes. And maybe the onboard GNS would measure the positions having some errors, or the configuration errors, or some signal receiving error, whatever the or constellation issues, or exceeding, go beyond the critical distance, or whatever the things also. And the other thing is when the aircraft is flying a very long strips, with very long strips, after certain distance, after certain velocity, after certain distance, whatever the devices which is mounted in the platform tend to self-accelerated. Which is self-accelerated. IMU is self-accelerated, which is not able to accurately measure the relative accelerations. So that is contributors. It's also is known as the IMU or INS drift effect. Also the IMUs, these are the electronic devices, and the malfunction certain happens periodically, errors would arise, and also the interpolation errors also there. Okay. What are the other sources? And also once we get the data and the time of coordinate transformation, would have some errors happens in the utility instruction. So these are the basic error sources, and the if we summarize what are the sources: analysis scan, GPS, IMU, and the transformations. The consequence. What are the consequences? Actually, the consequences are influence to the excited positions. That is consequences. But you should also know that for the ranges or the elevation, it's mainly the elevation is mainly influenced by the position, GPS position, and also the ranges. These are the main two. For the planimetric errors, what contributes mainly by the scanner, whatever the angular measurements, scanner device, and also the IM. These are actually the both side error and these planimetric errors. Actually, these both side errors are maybe would be critical. Maybe sorry, maybe sometimes goes beyond degrees, which means it's a huge error. Because the both side is more critical than the lever. That's the main reason. The point cloud, the planimetric accuracy of the point cloud is less accurate than the elevation. So the elevation is the most accurate than the image data is in the other way. Okay. Some errors, the GNS errors, and some errors influence spontaneous in certain location, randomly happens, and some are throughout the strip, and throughout the entire block. For example, the diva or the both side. Okay. And though we can reduce some of the errors by doing calibrations and several other precautions, and if there are some errors exist and we may not able to seamlessly merge the data sets to get one single data sets. Actually, that similar to the photogrammetric survey or the drone survey, we may not need to maintain the several percentage accuracies. 20% is enough. It's just actually we don't want the overlaps, and we maintain overlap just to not to have any gaps between the strips. Otherwise, we don't want so then because of these issues, we're not able to get a seamless data sets. So kind of a mismatch within the overlap regions will exist. We can also minimize this by fitting the high order polynomials, and also we can do sort of kind of area-based matching or the feature-based matching and things. And say we can select one point from the point cloud relevant to one single strip. We can get a point which lie within the overlap region. For that particular point, we cannot recognize another point having the same location, because these two strips are captured by two different flight lines, and different. Since these are irregular distributions, we are not able to get the almost same point clouds and having but the near points can be fine. That's okay. So that instead of working with the single points, what we can do is we can select a bunch of points, a point neighborhood, also having the within a certain range, and we can get a similar type of point neighborhood having the same location within a certain region, say. And then what we can do is we can get a twin mesh of these two surfaces, surface areas, surface patches, and then we can overlay. And then we can do a least square adjustment until they properly match. This is how we can avoid or minimize these kind of strip mismatch strip adjustments. These are kind of a strip adjustment. Also, we can follow a kind of a feature-based matching. For example, the distinct features, for example, the ridge lines, the roof ridge lines. How do we get the roof ridge lines? We can get the neighboring roof planes. We can intersect them, these two, to get a 3D line segments. 3D line segment from one strip and another same 3D line segment from the other strip, and then we can match these line segments. Also, by least square minimization, we can adjust the strip adjustment, do the strip adjustment. So, okay. Now suppose our data is acceptable and free from the errors, and we can use these data sets for the reconstruction or the generation purposes. Okay, that time is running. So we should let me give a little time further. Actually, the world today, the tendency is to work with the third dimension. The reason is working with the 3D data is highly beneficial or highly helpful for better approximation than working with the traditional 2D maps. And also 3D city models are being increasingly used by the city planners and the cities, and even many cities in several countries. And several major cities like Berlin, New York, these municipal councils, city councils, sorry, city councils maintain their own the city models, and it's a tendency now. Okay. So what are the things which you could model? Actually, whatever the features on top of the landscape, we can model, and we can model the buildings, and we can model the trees, and we can model even the roads, and also the water features, and also even of course the terrain. We can straight away you can get the terrain. You don't need to model. That is something else. Okay. Here, this is what is given by the Airborne laser scanner is the top surface information related to the top surface. The beneath the features are also there beneath the canopy. That's okay, which is inside, but the top surface is given. That is the information related to the digital surface model. That is it looks like in the left side. And once we remove all these above surface objects, what is remain is the bare earth. That is the digital terrain model. The removing of unwanted things is a filter. Is known as filtering, and so we should have a kind of a filtering technique to get the digital terrain model from the digital surface models. Okay. Actually, it's obvious thing that the filtering is removal of unwanted things, and you guys already worked with the raster data, and you already do some kind of raster operations, and the filtering is also filter kernels you already use, and it's kind of a neighborhood operation. So from the raster you can get the neighbors, but how do you get the neighbors? How do you call the neighbors from the irregularly distributed point cloud? So that's the question. Actually, you can get the neighbors by following kind of point structuring method. That could be Dillon triangulation, or could be the voxels, or that could be the I would say the k-nearest neighbors, or several things are there. Actually, if one create a twin mesh and a 2D space, and in a way there should not be any point that lie on the circumcircle of any triangle of it. Then it's a triangulation, and you guys know this, as you can see. So then this triangle can be used to get to call the neighbors for the point A. The neighbors are BC and E, likewise. And also in the 2D raster, for a given pixel, we can recognize the neighboring pixels. But the point cloud is spread in the 3D volumetric space, and we should add the third dimension to the pixels, and that is, we should make the volumetric cells, that is voxels. So we can also use the voxels to recall the neighbors. And also from the point cloud, we can define kind of the distance for one selected point. For then we can find the neighbors. For each neighbors, can also again select define another distance, same distance, and this is how we can get the neighbors to neighbors, and likewise. That's all. Oh. What is given by the laser scan, Airborne laser scan, is the terrain surface features, and what we need is only the terrain features. So we should need to remove unwanted things. Okay, actually the point cloud is, which contains huge number of points. So the removal of the manual removal is consuming time, and is very cumbersome. And so what you should do is we should automate the filtering. And the automation, that is, we need some kind of computer algorithms. So just to simplify this filtering process, basically the algorithms rely on kind of the assumption, valid assumptions. We need only the terrain. Terrain are the lowest points from the point cloud. If there are nothing below the terrain, the lowest points belongs to the terrain. There is one valid assumption. And also I would not say everything because of the time constraints. So and also bare earth can be considered as a piecewise continuous surface. It's a very valid assumption. So we'll move further quickly now, and we can recognize from the point cloud. Let me take 2 consecutive points. If the elevated point, there's a tendency to the elevated point to belong to the off terrain point objects, not the terrain. How do you test it? Generally, if you choose the 2 points, there's a distance between the Euclidean distance between the 2 points. There's a vertical separation, and the vertical separation increase by increasing the distance. Also, these are a good measure. Say if we assume the slope of the terrain is not steeper than 30%, that's 0.3 t, which is what we need to test with the elevation. Okay, then we can recognize if the things if the neighbor falls within the threshold, the neighbor one is also belonging to the terrain, otherwise off terrain. So once we do the filtering, this nicely will get the bare earth containing the ditches and everything nicely. These are another efficient, another kind of filter algorithm. The height layer analysis, actually this is this modified one is developed by my colleague Nalini, who works also colleague in the faculty, and she's doing her PhD in Germany. Actually what we can do here is we can, from the point cloud, we can find the bounds of the point clouds, the boundaries, the horizontal and the vertical boundaries, and then we can split the vertical split into several height layers, and also the vertical is what we can get is at the end we'll get kind of a vertical kind of columns. For each column there are several points, and generally it's an obvious fact that the higher number of points, generally the largest feature is the terrain, which means large number, there should be large number of points. These points should be the lowest points. If we make a histogram of that column, if there is a lowest peak, then these points will belong to the terrain. That is very, very valid assumption. By doing so, we can classify the point to either terrain or the vegetation, terrain or the off terrain. Okay. Also, we can fit the surfaces, and from the average surface, yes, we can first make an average surface, and then from the average second we can find the residuals, and the lower points would use the negative residuals. In a way, we are assigning the weights, higher weights for the negative residuals. The points having the negative residuals will get more influence from the low points. These are one way to speedily bring the surface to the top of the Earth surface. This is a summary, and you can nicely remove these points. And this another one is the twin densification, starting from your point cloud, starting from the all four corners. By selecting the lowest point of corners, four corners, we can generate a twin mesh. That is that we can get the two triangles, and by densifying the triangles, by adding the points which obeys the defined criteria, then we can densify. At the end, there's no points to be added to the twin mesh. This what we get is the terrain surface. Okay. Here. Okay. Sorry, I don't have the thing to run this little video here. We'll move further. Other thing. Okay. What I'm talking so far is the removal of unnecessary points based on the points, considering the points. We can also remove the point segment as point patches at once. To do it, but first we should do the segments, point segments. First we create the point segments. How do you create the point segments? There are several approaches there. The one is the scanline segmentation. First, we can split your point cloud into several directions. Say, you can split your point cloud along 3 directions. Say, so these are the scan lines. Let's say, and within the scan line, the points which lie within a certain plane, within the same plane, we can connect everything. This is a profile now. Profiles lie on one single plane. These are kind of 3D line segments. Okay. Then what we can do is by merging these profile layers, then we can merge the line segments belong to the different layers as long as they are lie within the same plane. This is how we can draw the planar patches. Here, these are the examples. These are the scan lines which are classified, and once we merged, what we get is the planar patches. And the next thing is to classify the segments itself, either to terrain or the non-terrain. Just by doing kind of a geometrical analysis, whether it is raised or the lowered or whatever, then we can easily classify either to terrain or the off terrain. Okay. We could also use the kind of a drawing technique. Actually, in raster data, we could use region drawing to make the segments. How do you do the regions? Starting from a seed pixel, we can grow that pixel until there are no more point pixels to be added. In a similar way, starting from the seed, generally in the point clouds, features represent the planar faces. So then we need to grow the surfaces. Starting from the seed plane, we can grow it. How do you grow it? Plane has a normal vector. If in a twin mesh, if the vectors have oriented in the same direction, we can nicely merge and nicely draw. Or starting from the seed which we derive plane, we have a plane, and within a kind of a buffer zone, sort of a zone, we can add the points lie within distance, within a certain distance. These are the way we draw. But the thing is the selection of the seed. If we select the base seed, we nicely get a nice segment. Otherwise, we'll get a worse or the wrong results. So then the issue is to get the seed surfaces. To get the seed surface, we could use the 3D half transforms and the ransack, and these are the random sample concepts, and these are the two the efficient algorithms to draw the surfaces, the seed surfaces, not the draw, the seed surfaces. And actually, what is just in the ransack is yeah, in the case of 2D lines, let's say in the case of lines, that is more easy to understand. Starting from the minimum number of points, that is, we need only 2 points to generate a line. And then we can compute, we can let the ransack to compute the compatible observations. That is, the compatible observation means the number of constants. Okay. The one which provides the maximum number of constants would be the best seed. For example, here I have chosen these red points, 1 and 2. These are the seed, my 2 seeds. So then this is my line, and then what are the lines which falls within that line is very less. If I choose the seed as in these 2 seeds points, in these 2 points, then what we get is nicely the several points would lie within the seed, this line segment. That is, this would be the base line, which means this is the base seed. This is how we can get the seed surface, and we can also draw, again, end up with the surface drawn one. These are the results of region growing itself, only itself. This is with the region growing, the growing by ransack. This gives nice result, and this is several over segmented, several patches, small patches would be there. There's no something like that. The other one is the half, in the polar coordinate system, and I'm not talking about the 2D lines. In the polar coordinate systems, the lines can be described. Line can be described in a way x plus alpha with the angle and the distance. Okay. Through this point, there are several lines would exist. In the half space, the several lines, or the infinite number of lines, these infinite number of lines would represented by the sinusoidal curve. Whatever the location at the curve, which indicates a specific line. Okay. Say, let me take another line passing through this point. Then we'll get another curve. I'll get another curve. Several locations, I'll get several curves. If one time, if we get a location where the several curves intersect, that is a place. This is a place where this shows, this gives me a specific line. Say, passing through this one. Also, the second curve gives me this is relevant to the second point. That's means which we give the collinear lines, that is the line which passes through all the maximum number of points. That is how we get the maximum number of, that is the base seed. By modifying this into 3D, we can also find the 3D planar seeds. These are which look like from this is raw point clouds, and these clouds, not the rust, these point clouds. So once you draw from the 3D half transformation plus surface growing, we end up with a very nice segmented, nicely compatible roof plan segments. I should move further. Okay, and this since having number of segments are more cumbersome, and then we can, it's nice thing if we can merge all these segments and make one single segment to represent the entire building, or the entire, then which minimize the number of segments as well. Also, we can get a very large segment for the basically for the terrain. Okay, so then what we need to test now is to discontinuation between the segment and the neighbors. What we do is, and along the boundary, we can check that it's continuity. If it is elevated along the everywhere, then for sure this is an object. Actually, this is which is developed by during my masters, and these are some results which I obtained. I would go further, and this is a kind of a classification, similar to raster classification. How do we assess the classification accuracy? By the confusion matrix, for example. Similar to the raster confusion matrix, we can also form the confusion matrix for the point classifications. Here, since we have only two classes, that is the terrain and off terrain, we may have only the two errors. That is, say we can say these errors as type 1 and type 2. Type 1 error is the misclassification of bare earth point as object points. That is the error 2. Second error is the type 2 is the misclassification of object points as the bare earth. So there is an unclassified points remain in your data sets. You can also define another error type called the type 3, and because from the unclassified points, certain real bare earth would remain as unclassified, which is an error. Also, real object points would remain as unclassified. It's also an error. Okay, so we can also visualize the errors with by assigning different colors to the point cloud. This is right, and also when reconstructing the 3D topography, we should also you should know something about the level of detail. That is, let me consider the buildings. The lowest level of detail is a level of LOD 0. LOD 0 is no third dimension; it's 2D maps. The LOD 1 is just box model buildings. Almost all the buildings are flat roofs. Actually, there is no flat. I mean, there are several. I mean, the gable and slant roof buildings, but the LOD 1 represent these everything as box type. LOD 2 shows the real the roof shapes, and the 3 shape provides us the rooftops features together with the roof shapes, and the LOD 4 shows, in addition to the facade, everything, facade information as well. This is a kind of example of the LOD 3 building model, city model, together with the vegetation, trees. How do you reconstruct the buildings? That's another question. And the buildings can be reconstructed with the help of predefined building shapes. Actually, the predefined building libraries, shape libraries. What we could do is to bring one predefined model and fit it, check whether it fit with the data, your candidate point cluster. If the one which provides the least number of error is the best fit model, and that is which means that represent the building type, the chosen building type. Here, these are the shed roof, gable, and hip roof, pyramid, the mansard, and non-symmetrical gable, and several building types. And we could also use the softwares, there are specific softwares to reconstruct or to do this matching, best fit matching. Okay, and the issue of this method, the model driven, since we are rely with the sort of predefined models, we call this as a model driven. The issue of the model driven is actually all these models may not characterize each and every types of building shapes. The lack of models is the barrier. Because of that, we should go for the other ways. These are the data driven. Data driven, which means we rely with the data, whatever the features, everything should be extracted from the data. Okay, from the point cloud, first we should extract the features. From the extraction, we can reconstruct the building geometrically, actually the roof, and then we can add the walls to that. Then can complete the 3D roof models, 3 building models. Okay, here this is the point cloud. This is the plan segmentation results. So then this is the once we need only the roof. Our objective now is to get the roof. To get the roof, we should select the roof from the off terrain points. Okay, then that is first we should do the classification. As we have already done it and talk about it, and then from the after points, after end segments, we can recognize the building segments. How do you find the building segments? We should we should test several rules, several constraints. One thing is kind of a gable roof. There is the gable roofs are having the symmetrical slopes. There is a symmetric slope symmetricity is there. Also, the hip roof. This is an hip roof, part of a hip roof. In the hip roof, there's a gable two roofs, and these are the hip parts, and the azimuth angle direction along the steepest slope direction is the azimuth. Azimuth angle in the hip case, in the ridge case, is the almost 100, nearly 100. Sorry, the 180 degrees opposite directions, and this is the 90 degrees. And the ridge line is horizontal. In this case, this ridge line is kind of yeah. Also, we can define some angles, and in this case, the 60 degrees nearly. By applying certain constraints, we can extract the roofs. Then from these roofs and adjacent roofs, by intersecting adjacent roof, we can get the ridges. Now we have the roofs, and we can have ridge is the one feature, the 3 lines. Also, we can get how we get the gutters. We can also find the lowest point from a particular segment, and then we can pass vertical roof, sorry, the vertical surface, planar surface, through that point. Then we'll get the gutter. This is an intersection of 2 planes, and intersection 2 planes leaves us one single 3 line segment, that is the gutter line. Likewise, we can get all these boundaries by intersecting the planes. Plane intersection gives us the boundaries, but the issue is how do we nicely recall these boundaries and get nicely make the topologically correct the wireframes to recall the features and things, and we need to get some kind of the other additional concepts. And actually, I developed I used the graph theories to get these the ridges or the feature lines, and the idea is to, by geometrically fixing the roof corners, we can finally end up with the 3D roof. How do we find the ridges or the relevant to this corner is we need to recall these ridges. We can recall the ridges with the help of these cycles. So from the graph cycles, cycle graphs, we can do a kind of a least square weighted least square adjustment. We can get nicely fix these corners, or otherwise we can, with the help of by working with the original roof planes, we can also intersection of 3 points also gives us a one single points least square adjustment. We can get one nice geometrically correct things. These are the ways which we could follow. And how do we get the outer lines, the eaves or the gutters? Actually, these are twin mesh, and from the mesh we can get the outermost edge, also known as the contours, and then from the outer edge, and we can fit line segments, linear line segments, and then we can regularize these line segments would orient in different directions, orthogonality, and we should choose to decide one dominant direction. That is could be the ridge lines, direction of the ridge line parallel to the ridge direction, and orthogonal to these eaves and gutters can be reconstructed. And so here are some nicely reconstructed rooftops, and these are some results of that I got from while I'm doing PhD. And these are the nice 3D buildings of Fahingen, Germany, and this is how we can reconstruct the vegetation. How do you reconstruct vegetation here? Actually, the vegetation are reconstructed by my colleague Nalini. She also analyzed the same concept, is height layer analysis, and the data set by height layer analysis in a certain locations will get highly dense. Once we project all these height layers, all these the stem points will projected on a certain clustered location, that is high density points is given. These highly dense locations are probably the one stem location. Recognizing the stem locations and then drawing the stem will nicely get the type of stems. Having the knowing the stems, what we now remain is to recognize the leaves or the split or the classified leaves belong to each individual stems. That can be generally the crown is spread within a certain range, and by applying certain angular and geometric constraints, you can split, isolate each and every point clouds into individual respective stems. So these are some examples of that. And here actually I referred several other materials. The Klaus Brenner is talks and also his materials that he used, also the thesis of Nalini, and also George Wilson is my supervisor, master supervisor, and also several other things. And if someone is interested to work and to know something more about the laser scanning, and I would recommend, this is nice. I mean, simply explain that is written by me in about laser scanning and principle of processing principles. With my colleague, you could also refer this. And so now, any questions? So I would have to answer. Hello.
Thank you very much, sir. So this is Q&A session. If you have any issues regarding this session, you can put forward your question.
I think the people are tired, feel, and maybe a bit more. I'm not sure whether it's people got the things. I would explain things as much as in a way, simple way. I think no questions. Maybe we can wind up for the.
Okay, so let's wind up then. Thank you, sir. Actually, thank you very much to this guest speaker, Dr. Sanka and Perera, for dedicating your valuable time for us. I believe that it was really an informative and effective session. So, on behalf of all the participants, I really appreciate this efficacious session, and I'm very much grateful for all the participants for their attendance today. So, hopefully, we will meet with another interesting and valuable session like this in your future. And until then, stay safe and see you soon. Thank you.
Okay, see you. Okay, bye.